All right, everybody, what's up? So I had to go live. So this is where we ended up last time. We did that problem right there. So let's continue with the chemistry. And let me know if you guys can hear me. Because I was scared that I did the physics earlier. I was scared I didn't have the audio, but it looks like we did. So, anyways, let's continue. We're at chapter 3.3 on the chemistry. And so let's go. All right. All right. So chemical formulas and chemical equations both have a quantitative significance. The subscripts and the formulas and coefficients in equations represent precise quantities. The formula H2O indicates that molecule of the substance water contains exactly 2 atoms of hydrogen and 1 atom of oxygen. Similarly, the coefficients is balanced chemical equation indicate the relative quantities in each reaction and products. But how do we relate the number of atoms directly account atoms and molecules? We can indirectly determine their numbers if the chemical formula and the equations must examine the masses of atoms and the molecules, which we in the section in the next. Wait, hold on, guys. My dog keeps barking. Hold on. All right. So thank you for waiting. All right. So I guess we're right here. So I was looking at the problem right above. 3232. Oh yeah, we already did that. Okay. All right. So formula and molecular weights. The formula weight is a substance is the sum of the atomic weights of each atom in its chemical formula. Using the atomic masses from a periodic table, we find, for example, that the formula weights of a sulfuric acid H2SO4 oh, SO4 is the 98.1 AMU atomic mass unit. A formula weight of H2SO4 equals 2 atomic weights of hydrogen plus 2 atomic weights of sulfur plus 4 atomic weights of oxygen equals 2 1 AMU plus 32.1 AMU plus 416 AMU, 98.1 atomic mass units. All right, the way they got those numbers is through the periodic table, which is over here. And just these are the weights right here, right underneath the big number, okay, or the letters. What the fuck? All right, there you go. All right, so for convenience, we have rounded all the atomic weights in one place beyond the decimal point. We will round off the atomic weights in this way for most problems. Uh, if the decimal formula is merely the chemical symbol of the element, such as Na, then the formula weight equals the atomic weights of the element. In this case, 23 atomic units, and the chemical formula, the mole, then the formula weight is also called molecular weight. The molecular weight of glucose C6H12O6, for example, glucose is sugar, if I'm correct. Molecular weight of C6H12O6 equals 612 atomic mass units plus 12 1 AMU plus 16 atomic mass units equals 180 atomic mass units. Because ionic substance such as sodium chloride exists as three-dimensional arrays of ions, it is inappropriate to speak of molecules of NaCl. So, so remember when I said sodium, we're already talking about like ocean water and salt. All right. So anyway, let's flip the page. All right. So instead, we speak of formula units represented by chemical formulas of substance. The formula NaCl consists of Na plus ions and sodium ions plus chlorine ions. Thus, the formula weight of NaCl mass formula unit uh, formula weight equals 23 AMU plus 35.5 AMU equals 58.5 atomic mass units. Uh, so calculating formula weights, let's say calculate the formula weight of sucrose, and then this should be easy. We're gonna do this quick, guys, because my dogs are barking. So we're gonna stop at 3.4, which is pretty much right there. All right, so sucrose, we got C12 H22 and oxygen 11. So we just got to find out what the weights are for these guys and then multiply by that big number right there. So we got 12 times whatever carbon is. You see that? Plus 22 times whatever the weight of hydrogen is, plus 11 times plus 11 times whatever the weight of oxygen is. I remember carbon is 12, I think, but let's check. And hydrogen is 1 and oxygen is 16. But I might be wrong. Oh yeah, I think that is right. I'm out cheating now. I'm looking at the book now. You see that? That should be right. So what's 12 times 12? Well, whatever this equals, I guess it equals 342. All right. See that? So what's happening, just so you guys can know, 12 times 12, I think that's 144. 144, 22. What's 11 times 16? So times 10 will be 160 plus another 16. We're at 176. And that should equal 342, I think. All right, go double check that shit, guys. Oh shit. I'm not even showing you guys the whatever I'm doing. That sucks. I did that whole shit and didn't even show you what I was doing. God damn it. But anyways, that's where we're at right there. All right, percentage, composition, and formulas. Occasionally, we must calculate the percentage composition of a compound that is a percentage of a mass contributed by each element of the substance. For example, to verify and purify a compound, we can compose and calculate percentages composition of a substance found experimentally. Forensic chemists, for example, will measure the percentage of a composition with an unknown uh, white powder and compare it to percentage composition of sugar, salt, or cocaine to identify the powder. Calculating percent composition is a straightforward matter if the chemical formula is known. The calculation depends on the formula weight of a substance and atomic weight of the element of interest and the number of atoms that the element of the chemical formula. Percent element equals atomic atoms of the element multiplied by the atomic weight of an element divided by formula weight of the compound times 100, and it gives you the answer. There you go. All right, so let's get another one. So it says calculate. Oh wait, you know what? We didn't finish the other one. Oh shit. All right, we forgot to do calcium. What is it? Calcium nitrate or calcium? Yeah, nitrate, NO3. All right, so we gotta figure out how many calcium atoms there is. So we know it's one. So it'll be one times whatever the formula weight of calcium plus two, because I'm multiplying it right there, of nitrogen plus six oxygen, which I know is 16. All right, you see that? So nitrogen, just because we're gonna cheat a little bit looking, it's 14, and calcium is 40. I'm looking right there. It says 40.1, so I'm gonna put point one. See that? And then you get that answer for that. There you go. See that? So this should equal 40.1 plus 28 plus what is it? What's 16 times 6? 72, some shit like that. And then this whole thing equals 164.1 AMU. All right, so we solved that shit. All right, next one is so it says calculate the percent of carbon, hydrogen, and oxygen by mass in C12 H22 oxygen 11. Okay, you see that? Mm-mm-mm. All right. Okay. So first up, let's just continue what we're doing, right? So to solve, we're going to go 12 times whatever the weight of carbon is plus 22 of the hydrogen plus 11 of the oxygen equals. Okay, see that? So that's 12, 11, and 16. I remember that. Um, oh, no wonder we already did this problem. It's part of the previous problem, 342. See that? 342. 0.0. Okay, so we got that part of the problem. So now all we got to do is, since we got the percentage, now we get the carbon. So we got 12 carbons. Now we'll want to get the percentage of each one. So we got to get this number divided by this number on each one, and you get the percentage. So we get the percent of carbon is equal to 12 times 12 AMU, or atomic mass units. So the weight. So this, yeah, these two is the same. They go there, and this one goes right there. See that? Let me just put 12 divided by 342. times 100% equals 42.108 when you plug it into the calculator. Okay. And that's for carbon. And then for was it? For hydrogen, it's the same shit. Only instead of right here, you put hydrogen, and then you're gonna put there's 22 of them right there. Okay. And it weighs one. See that? Over 342 because it's the same molecule. See that? Times 100 because you want the percentage. And that's going to equal 6.43%. Okay. And then you do the same thing for oxygen. I'm trying to copy and paste this and I can't. All right. So now that's not the problem though. All right. So now we do the same thing for oxygen. So for the percent of oxygen is equal to 11 times 16. So look at the periodic table and then the weight right here times 100%. And that's going to equal 51.46%. Okay. And that's how you solve that. And then we're at Avogadro's number. And then that's where we're going to end it, guys. And we're just going to do the last practice exercise. All right. So that's the last one. So, moment of truth. So it says calculate the percent of nitrogen by mass in calcium nitrate. All right, so percent of nitrogen. All right, so let's do the same thing. So 1 times calcium. What's calcium? 40.1. Oh, we already did this one too. Okay, perfect. So yeah, that's gonna help a lot. Okay, so 40.1. All right, you see that? Plus 2 nitrates, because multiply this by 2. 2 times, what was nitrate? 14. Plus 2 times 3 is 6. So you get 6 plus 6 oxygens. And oxygen weighs 16. If you look at the periodic table, and that's going to equal to 164.1. You see that? And then they want you to calculate the percent of nitrogen. All right, so we know nitrogen is 2. So you get 2 times it weighs 14. So you get this part. It's basically gonna go down here. But don't do it like that. Just look at, always go back to here instead. Focus on this. All right, you see that? And then we're gonna divide it by 164.1. See that? Oh, and then multiply it by 100 because you will want the percent. And that's going to equal, if you plug it into the calculator, 17.7%. Okay, see that? And then if you round it, you get the answer from the book. All right. And then you get that. All right. So we're going to end it there. We're going to end it off at Avogadro's number. And that's going to be for next time. All right. So thank you guys for watching this quick clip. And I'll see you guys on the next video, on the next live.